In this lecture for chapter 27, I want to talk about RC circuits, resistor capacitor circuits. So there's just two elements in the circuit besides the battery. But before I do that, I wanted to mention something I forgot to talk about. They talk about in the book a fair amount, called internal resistance. So, and electromotive force. So basically, when you have a battery, you have a voltage. So if you take a 9-volt battery, you might get 9 volts across it when it's not in the circuit. When you put it in the circuit, the voltage across the battery will be a little bit less than when it's not in the circuit. And that's because it has some internal resistance inside the battery itself. So when you hook it into the circuit and you end up doing kind of a Kirchhoff's loop rule thing, you get the voltage between the terminals of the battery, you go across this internal resistor or internal resistance. So instead of the 9 volts when it's not in the circuit, when it's connected, you get the voltage between the terminals as V minus IR, right? So whatever the current ends up being, that'll depend on other resistors in the circuit. But there's this voltage drop due to the internal resistance. And in fact, in the book, they will call this E, or electromotive force, quite often. So I just wanted to talk about that briefly. Let's go on to the topic of RC circuits. So in an RC circuit, we have a resistor and a capacitor, an R and a C. We've got our electromotive force or voltage from the battery, whatever it is. Here I have a switch. So what I can do is put it in position A, push it up, and that will charge up the capacitor, right? Because now I'm connected to the battery through this circuit. Once I get the battery charged, I could push the switch down to B, and then the battery's out of the circuit and the capacitor will discharge. All the charge will flow off of it from one plate to the other. In either case, you're going to get a current for a period of time as the charge either builds up on the capacitor or leaks off. So let's talk about the charging capacitor case first. So I've put the switch in position A, and if I use the loop rule, right, starting behind the battery, maybe going around the whole loop, I get this equation, E or B, or electromotive force of the battery, voltage of the battery, minus IR. Now I go across the capacitor and there's a certain amount of charge Q, voltage is Q over C, so I get minus Q over C as I go across that battery. It's a voltage drop there. So one thing to remember too is current is the derivative of the charge. So plugging that in, I actually get a differential equation for the charge as a function of time. So it's not going to go in necessarily a simple way. And I'm not going to go through the way of solving this right now. What we'll do is just assume the solution. You can prove it by just plugging it in, right? If you take the Q that I have here and plug it in all the places in the differential equation, take the derivative, you can show that this is a solution. But the main thing is that I wanted to show is that the charge grows with an exponential type of behavior, right? It actually grows really quick and then starts to slow down as more charge is on the capacitor and kind of pushes back. So eventually you get to very, very long time and the capacitor reaches its full charge, which is CE or CV of the battery. One thing you'll notice in the equation for the solution, there's this resistance times capacitance, and we call that the time constant of the RC circuit. For example, when you plug in that time, RC, right, the T over RC becomes 1, and you get 0.63 CE. So what I can say is that the time constant tau is the time for the charge on the capacitor to increase from 0 to 63% of its final value. So it's the time to get up to 63% of the final charge on the capacitor as it charges up. Okay. So now let's say I've got it in switch A and I've fully charged the capacitor. I've waited a long enough time. Now I'm going to switch down to B. At that point, all of the charge in the capacitor is going to go the other way as it discharges. Right? And you could say I've stored energy in the capacitor. Now it's going to go back and show up as heat in the resistor, or maybe you put another device, maybe a lamp that will flash or something while this capacitor discharges. So as we have a discharging capacitor, we start with a certain amount of initial charge, which is equal to the maximum charge that we put on it by charging it, C times V0, or whatever that maximum voltage is. But we've switched it and taken out the battery. So the electromotive force of the battery is gone. We get this differential equation if we use the loop rule. Now you can kind of think of it as a positive voltage, right? It's actually pushing the charge off of the capacitor. Again, not going through, but maybe you can easily see that we should get an exponential decay of the charge. Charge leaks off really quickly, but then more and more slowly the rest comes off because there's not as much voltage from the capacitor pushing it off anymore. But this is the equation we get. Q of t is the initial charge, maximum charge, times e to the negative t over RC. So again, we have that time constant in there. You can also get the current as a function of time just by taking the derivative of Q of t, right? And you get negative Q0 over RC, e to the negative t over RC. So this is the initial current that you start with when it's at its maximum charge. And again, the current decays away exponentially as well. So hopefully that will help you answer questions about discharging the capacitor. At this point, we're kind of done with circuits. The next subject will be magnetism and magnetic fields. But we'll stop at that point for chapter 27.